So now we should have had a chance to go over and try some of these questions on intermolecular forces. So let's go over them. And we can do these in any order, but sometimes with these I like to start sort of with the easy ones. And the two easy ones to me are D and E. Why? Well, both of these are ionic compounds. And we know that for ionic compounds we're going to have ionic type intermolecular forces. The other one that's probably the easiest is the hydrocarbon, part C. We know hydrocarbons are completely nonpolar molecules which predominate with London forces. We also might find that F, because the electronegativities of these two elements are almost identical, that we find London forces here as well. Part A, ethanol, has an OH group, and we know that OH, NH, and FH will all have hydrogen bonding. And then our last two, HCl and sulfur hexafluoride, are both compounds that have elements that have very different electronegativities. And when the electronegativities are very different, the dominant force will be dipole-dipole. Or I should say different, but not so different that we get an ionic compound. So now we have some groups of compounds that we need to rank from highest to lowest boiling point. First of all, let's ignore this. So how would we rank them? Well, we're largely looking at differences in electronegativity. Now, initially that you might expect we're just going to start nitrogen trifluoride as the biggest might have the biggest difference. But it turns out that's not the case. And then we just go, fluorine, chlorine, bromine, iodine. Now, while it's true that NF3 of this group will have the biggest electronegativity difference, they then rank, if you look at electronegativities, as iodine, bromine, and nitrogen trichloride, which it turns out nitrogen trichloride has almost no difference in electronegativity. So as we go in this direction, we have an increasing difference in electronegativity. In our next example, we now have all different types of intermolecular forces at play. So we have two compounds, methane and octane, that are only van der Waals forces. And so we would rank those as methane being the lowest, followed by octane. And we choose this order, again, because both of these only have intermolecular forces, meaning they're both very nonpolar compounds. But in addition to that, octane being a longer chain than methane is going to have a higher boiling point than methane. Next, at the opposite end, we're going to have cesium carbonate. Why cesium carbonate? Well, cesium carbonate is an ionic compound, and we know that ionic compounds have extremely high boiling points, or melting points. So then it just becomes a matter of what's going to be higher of what's left, ethanol or chloroethane. And if you think about the properties that those two compounds have, chloroethane has dipole-dipole interactions, whereas ethanol, because of the OH group, has hydrogen bonding. And we know that hydrogen bonding is a stronger force than dipole-dipole. So ethanol should have a higher boiling point when compared to chloroethane. Now, solubility is something that we're going to address more in the next chapter, but we're going to get a short introduction to it here and see if we can apply what we've already learned to this situation. So what kinds of compounds do you think would be soluble in water? Well, the issue is water itself is a very polar molecule. And so what will be attracted to water are other polar molecules. So if a molecule is very polar, such as an ionic compound, we would expect it to be water soluble. Same thing with anything that has hydrogen bonding like ethanol or acetic acid. And so would a compound with a pretty strong dipole like hydrochloric acid. The last two compounds, which are very long carbon chains, these are not going to be water soluble. But again, that's something we'll discuss in much more detail in the next chapter. Finally, we have two pairs of compounds here that have similar types of intermolecular forces, but one's going to have a higher boiling point than the other. So in the case of propane and octane, these are hydrocarbons. There's nothing polar about them. So these are van der Waals forces, or London dispersion forces. In the case of both propanol and octanol, we have that OH group, and so we get hydrogen bonding. Which one has the higher boiling point? Well, in both cases, it's the longer chain. And it's the longer chain because having that longer chain, regardless of what other forces are present, that longer chain allows for additional van der Waals forces.